much of the final for you as I can. So let's, before we get too involved with the final, why don't we wrap up homework 12 because that is due the day after tomorrow on Wednesday, end of day. Are there any questions about homework 12? Can we go over question 4? Yeah, sure we can. Just a minute. I'm going to pull it out right now. Got it here in front of me. Question 4. Oh my goodness. Question 4. Okay, well. In question 4 we have a rather large-ish looking table. And what we want to do here is we want to try and come up with a fully reduced state table. And so in order to do that, we need to... This looks very familiar. Didn't we do this already? Didn't we do question 4 once? No? Okay. Well, if we didn't do it, I will do it. If we did it, then maybe we should move on to something new. No? Didn't do it? Okay, then we'll do it here. For some reason, I thought we did it. I've recorded all of my extra help sessions and also prior... oh, you didn't finish it. Okay. Well, then let's see if we can finish it. Present state is A through K. Next state is going to be for xy at 0, 0, 0, 1, 1, 1, and 1, 0. So it's quite long. BBHH BFJE IBA. And then it says ICG. Then it says CFG. So that's an I. Then it says let's see, DDF, CEG, CIG, IIK. You know what? I don't think I got that right. Let's take a look. This is a problem because if you transcribe these things incorrectly, it will be wrong. So let's just see where we are here. There's I, C, D, C, C, I, K, F, I, F, C. All right, let's go to the next row. CFDE, CFDE, I, G, C, I, C, D. That's E. Wait a minute. What are we looking at here? K, A, C, that should be E. All right. And then G, G, F, G, 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 F, G, G, K, H, G, D, G, G, G. And then the output is going to be 0, 0, 1, 1, 0, 0. It's all 0. And that's it. And now what we need is to get the fully reduced state machine. So we start with B and work our way to K. And now we're going to start with A and work our way to J. Is there a question out there? Somebody's got their mic open, I think. Oh. And now I'm switching to lined paper instead of graph paper, just on the idea that maybe these implication charts will get a little bit easier to read. A, B, C, that's supposed to be a D. So this is the same exact technique we used before. It just got a little bit more cluttered because we've got more inputs and we've got more states. I think that looks about right. So we started with the first letter and ended with the penultimate letter. Started with the second letter and ended with the last letter. And so that's how you do that. And now what we want to do is see where outputs are different. So A, which is 0, is different from C, D, and K. And B has an output which is different from C, D, and K. And C has an output which is different from E through J. And D has an output which is different from E through J. And E has an output which is different from K. And F is different from K. And G is different from K. And H is different from K. And I is different from K. And J is different from K. And that's what we got. So now, let's take a look at A, B. When we compare A and B, B has to be equal to B, so that's pretty good. I has to be equal to C, so that's C, I. We know those are not equal, so that goes out. When A is compared to E, we know B has to be equal to B, C has to be equal to I, but we know C is not equal to I, so that goes out. We compare A to F, we see B has to be the same as F, we don't know. I has to be the same as I, that's good. C has to be the same as I, that we know, we don't have. So then we go A to G, so B has to be the same as J, we don't know. K has to be the same as I, and it isn't, so that gets nuked. Then comes A to H, and we compare B and E. We don't know about that one. We compare I to F, and we don't know about that one. We compare C to C, that's all right. G to G, yep, that's good. Outputs are the same. So in our comparison between A and H, we're interested in BE. Let's chase that one down. So B compared to E. If B is compared to B, that's good. C is compared to C, that's good. I is compared to F, we don't know. So really, if you think about it, it all depends on BE, and that depends on IF. So BE is an IF dependency. Or you could say FI if you want to go in alphabetic order, which is normal. Let's look at FI. So FI we don't know. Let's chase it down. So FI is true if FI is true, so that's good. If I is equal to I, if I is equal to I, if K is equal to D. Now let's take a look at that. We don't know about K and D. So it's really kind of dependent on K and D. Or you could have said DK, I suppose. So then let's look at DK. So D is compared to K is true if A is compared to B, but it's not. So that doesn't work, which means I is not equal to F because F requires D and K to be equal. Isn't that right? And yes, it is. So this can't be true. So if FI or IF are not equal, then we know BE is not equal. And if BE is not equal, then we know AH is not equal. So we just backed out a whole bunch of squares just by doing a deep dive exploration. Let's look at AI. AI is true if B is equal to I. I don't know about that one. I is equal to I, that's good. C is equal to I. Now that one we know we don't got, so we nuked that one too. Then comes AJ. A is compared to J if B equals B. If I equals F, we happen to know that I does not equal F, therefore this is out. B is compared to F, that's this square here. So let's compare B and F. So BF is true if BF is true, and is true if CI is true, but we happen to know that CI is not true, so this goes out. B is compared to G, is true if B is equal to J. We don't know about that one. If C is equal to K, we don't know about that one. If F is equal to G, we don't know about that one. Wow. If G is equal to H, we don't know about that one. So this BG thing is a complete mystery, but it seems to depend on GH, at least in part. So let's go hunting for GH. That's down in here. G is equal to H if J is equal to E. We don't know. If K is equal to F, no, it's not. K is not equal to F. So what that tells me is G is not equal to H. So if G is not equal to H, this gets an X, and this gets an X. So now let's go on. How about B and H? B will be equal to H if B is equal to E. B is not equal to E, therefore B is not equal to H. About B and I. B is equal to I if B equals I, that's all right. If C equals I, well, now just a minute. We know that's not true. B is going to be equal to J if B equals B, that's good. If C equals F, nope. Now we go to the next one. C is equal to D if H equals H, yep. If C equals D, okay. If D equals E, no, D does not equal E. So C equals K if A equals H, but it doesn't. Let's see, E equals F if B equals F, and we know it doesn't. E equals G if B equals J, and it does not. E equals H if B equals E, it doesn't. E equals I if B equals I, it does not. E equals J if B equals B, yep. If C equals F, it doesn't. Now we go on to the next column. F is equal to G. So I got GF if F is equal to J. We don't know about that. If I is equal to K. No, it's not, because this. And what about F and H? F is equal to H if F equals E. And we know it does not. Well, let's see. Is that true? E, F. Yeah, there's an X. So that means you got another X in here. What about F and J? So F and J, that's true if B is equal to F, but B is not equal to F, so we get another X. So we're really Xing everything out. G is equal to I if I is equal to J. Does I equal J? I don't know. If K is equal to I, does K equal I? No, it doesn't. So that gets X'd out. G is equal to J if B equals J, and it does not. H is equal to I if E is equal to I, and it is not. H is equal to J if B is equal to E, and it doesn't look like it is. I is equal to J if B is equal to I, and it is not. And so we have a reduced form. Now let's see. That is not the answer I got. Wow. So somewhere in here I must have made a mistake. But where that could be, is A equal to H? Let's see. A equals H if B equals E. B does not equal E. Yeah, so we can say that B is equal to H if, right? Oh, you want to say A is equal to H? A is equal to H if, and then we can write it out. B is equal to E. I is equal to F. Now, if I look up B and E, I get an X. And the reason I got an X is because I was not equal to F. And I determined I was not equal to F because I compared IF with IF, and then II, which is good, then II, which is fine, then KD. So I looked at KD, and K was not equal to D. Now, why wasn't... Okay, so I wrote that K was not equal to D, and K is not equal to D because A is not equal to H. Oh, it was self-referential, wasn't it? C is C, E, E, G, G, I. So actually, K is equal to D. Thank you. I missed that self-referential part. So K is equal to D. And if that's the case, then I is equal to F. Oh, boy. And if I is equal to F, then B is equal to E, I would guess. Let's see. B, 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 C, C, I, F, G, G. Yep. And then A should be equal to H. Oh, boy. That gives us a whole bunch of reductions. So that says A is equal to H, D is equal to K, F is equal to I, and B is equal to E. I wonder what other reductions we might have missed. Well, we'd have to go through. A is equal to J. Let's see. B equals B, I equals F, C equals C, G equals G. Yep, A equals J. That's good. So then we can put a check mark in there. And where else did we go wrong? Probably by the time we're done, we should have reduced by 1, 2, 3, 4, 5 states, which would give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wow, so maybe we're down to 1, 2, 3, 4, 5. Perhaps we're down to F, A through F. 1, 2, 3, 4, 5, 6. Yep. Yep. So, yeah, I take your point. You are correct. Let's do the following. J and H are replaced with A. K is replaced with D. I is replaced with F. E is replaced with B. And I think I is replaced with F, so that goes out. And what else? So we seem to have A, B, C, D, F, G. And that is what I have here, A, B, C, D, F, G. And it's BFCG 0, BFCG 0, there's the 0, BCFG 0, BCFG 0, ADD F1, ADD F1, yep, it looks pretty good actually, ACBG1, ACBG1, and this looks like AKH0. It says K. We replaced K, right? K was supposed to be D, was it? Yeah. See, here's K. It's supposed to be a D. I missed it. That's D. So that should be AD. Oh, and H was replaced, wasn't it? It was replaced with A. So that should be ADGA0 on line G, which is ADGA0. So that's correct. So that's a good problem actually, because I missed that self-referential part. Good spotting. Now, somebody, anybody? Yeah, sure. It's just the answer's A. But what has happened here is we did the substitutions that removed H and J and K and I and E. And then we ended up with that, which is, I think, consistent with this. Is that all right? Everybody okay with this? Can you move the screen over a bit? You mean like that? That was from earlier, sorry. Oh. Let me go back to the chat here and see what else is here. Can you do question 5? Someone writes. I'm doing these in order, the order in which they were requested on the chat. So are we okay with this now? Everybody all right? So let's move on. I'm liking this lined paper a little bit better. It's keeping things somewhat neater. So I think I'm going to continue with that for a little while anyway. So this is going to be question number 5. Let's see. Homework 12, number 5. And now, I think maybe we ought to take a look at the diagram here. It's kind of an interesting looking diagram. What I'm going to do is I'm going to encode this diagram into a present state, next state table, and then we can do the implication chart. So let's do that. But before I do, let me ask you a question. Is it a Moore machine or a Mealy machine? Mealy machine is correct. Yes, because the outputs appear on the arcs. That makes it an asynchronous machine. That is exactly right. So let's take a look at the present state, next state table here. This is too thick for me. And then we'll look at the output. And so the present state is S0 through S6, I think. And then you want to have x equal 0 for next state and x equal 1. So when x is equal to 0, it's S1, otherwise it's S4. If x is, if you're in a state 1 and you get a 0, it's S2. Oh dear. Looks like they're missing something here in the, right, that has to be there. And this has to be there. So we've got a couple of blemishes. That's too bad. And what should the outputs be? So then for S1, it's supposed to be S2 and S1. For S2, it's supposed to be S1 and S6. For S3, it's supposed to be S1 and S3. For S4, it's supposed to be S5 and S4. For S5, it's supposed to be S2 and S1. For S6, it's supposed to be, see, here's another blemish in the diagram. That should be labeled as a 0. And near as I can figure, for S6, the output should be a 0. So there's another blemish. I really got to fix that stuff. So for S6, next state should be S5 and S3. And then the outputs based on the input is supposed to be 0 and 0. And then it's supposed to be 0, 0. And then it's supposed to be 0, 0. And then it's supposed to be 0, 0. And then S4 is supposed to be 0, 0. It's all 0, 0. And then S5 is going to be 0, 0. Now S6 is different. S6 is going to be 0, 1. And that's what I got. What do you think of that? Does that look about right to everybody? All right, so first step, let's do the implication chart. And now it looks like S0 is different from S6, and in fact S1 is different from S6, S2, S3, S4, and S5 must be different from S6, all because the outputs are different. So the whole bottom row has got the X's in it. And then someone wrote, is S6 1? 1. No. And then they wrote, never mind. I said, okay. Now, let's see. It says here, I want to compare S0 with S1. So that's true if S1 equals S2. I don't know about that one. So let's write 1, 2. And also if 1 is equal to 4. Let's keep going. 1, 2 is true if 1 is equal to 2 and if 1 is equal to 6. So we don't know about, well, I don't have an S6, S1, oddly enough. Let's do another one. S1 is equal to S2 if S0 is equal to S1, if S1 is equal to S2, and if S1 is equal to 4. That we don't know. S1 is equal to S4 if S5 is equal to S2. You know what we should do is we should eliminate some of the stuff that's obviously, well, we don't know if it's any obvious. If there's any obvious ones. Let's keep going. S0 with S3 is true if S1 equals S1 and if S4 equals S3. Let's just write 3 and 4. S3 is equal to S4 if S1 equals S5 and if 3 equals 4. So S3 is equal to S4 if 1 is equal to 5 and if and 3 is equal to 4. So what about 1 and 5? S1 and S5, we don't know about that. So S1 and S5 are true if S1, if S2 equals S2, if S1 equals S1, hey, S1 does equal S5. So that's promising. Now let's take a look at S3 and S4. S3 and S4 are true if S2 equals S1. We don't know about that. And if S3 is equal to S1. We don't know about that either. So there's a lot of stuff we don't know here still. Let's take a look at S0 and S3. S0 and S3 is true if S1 equals S1. If S3 is equal to S4, we don't know about that. Yeah, I guess we got to keep going. S0 is equal to S4 if S1 is equal to S5, it is, and if S4 equals S4. So S0 equals S4. That's pretty good. S0 is equal to S5 if S1 equals S2. We don't know about that. And if S1 is equal to S4, we don't know about that either. So 1 and 4. Let's take a look at 1 and 4. 1 is equal to 4 if 2 is equal to 5. Two is equal to 5 if 1 is equal to 2. One is equal to 2 if if 1 is equal to 2, and if 1 is equal to 6. 1 is not equal to 6. Therefore, 1 is not equal to 2, which means 2 is not equal to 5, which means S1 cannot be equal to S4, because that depends on S1 and S4, and S2 and S5, and S2 and S5 we know are out, so therefore this is out. So now if we go back to S0, S3, we get S3, S4. We still don't know about S3, S4. That's S1, S5. That's okay. S3, S4, you know what? It is equal. So now if you go back to S0, S2, S1, S4, S6, oh, that's out. S4, S6 is out, right? Because here. So that's that was S0 to S2. That has to be out. How about S0 to S1? That's 1 to 2. S1 to S2, which is also out, right? Because S1, S2. So now let's take a look at S0, S3. S0, S3 is S1, S3. S3, S4 is okay. So that means this one's okay. So now we have S0 equals S3. And S3 is equal to S4. So that's kind of interesting. Let's take a look at S0, S4. I got 1 is, no, 1 is not equivalent to 5. Whoa, sorry, got a phone call here. Let me see what I can do to stop that. And then it says here S1 is equal to S3 if S1 is equal to S2, and it isn't, so we'll take that out. And then S2 is equal to S3 if S1 equals S2, and it's not. And then we have S1 is equal to S4 if S2 is equal to S5, and it isn't. Now we have S3 is equal to S5 if we have S1 is equal to S2. Here's S1. It's not equal to S2, so that's out. And we have S4 is equal to S5 if S2 is equal to S5, and it's not. So at the end of the day, this is what I have. Let's take a look and see what simplifications we can arrive at. So that says that S5 has to be written as S1 that S4 and S3 all get written as S0. So S4 and S3 are all written as 0. And that's all the reductions I could see. What do you think? Does that look all right? Any it says S5 is equal to S1. Yeah, that's what I wrote. Then it says, so S3 is equal to S4. Yep, that's correct. I think the answer should be the state machine is not properly labeled. That was long ago. Okay. Let's see. Is that an answer? The state machine is not properly labeled? None of the above. The state machine is not properly labeled. Yeah, that is an answer. Ah, boy. But we did reduce it. Had I labeled the state machine properly, you could get a reduction. So, yeah, the state machine is not properly labeled is a correct answer. And it is a selected answer, so obviously it's not properly labeled because it's missing critical transitions in through here and here. So that is correct. Homework number 5. None of the above. State machine is not properly labeled. But there is a reduction available if you label the state machine properly. But you have to know how to do it. So let's go back to the chat here and see what other questions we have. And somebody wrote, can we do question 8, 9, and 10? Can we do question 6 also? Question 6. Somebody wrote twice. So let's go to question 6, and then I guess we're going to get through as much as we can get through. So question 6. Were there any questions about question 5 before I proceed? No. Okay. I beg your pardon? Well, yeah. The answer is none of the above. The state machine is not properly labeled. Had I labeled the state machine properly, I think this would be okay. S2. Oh no, S3 is eliminated. Yeah, there may be a selection in here that is a correct answer if you know how to label the state machine. Let's see. S0, S1, S2. Yep, there isn't a correct answer available. So that is, except for the one that says the state machine is not properly labeled. There are none of the other answers even come close to the solution that I have created here, which I feel would have been fair if the state machine had been labeled properly, and it wasn't. So, life in the big city, moving on. Sometimes you get the bear, and sometimes the bear gets you. I don't even know what that means. So there you have it. Where are we? Oh, question 6. Homework 12, number 6. So what do we got? Let's have a look. There's this wonderful diagram, which is a little bit on the small side. And what I think I should do is maybe rewrite this diagram as a present state, next state diagram, and then present it to you. I think that's our best bet right here, because redrawing the diagram gives us limited features. So let's try it. Write a present state, next state based on that diagram. I am going to make it just a little bit larger so that I can see what's going on. Okay. First of all, is it a Moore machine or a Mealy machine? Moore or Mealy? That's a Mealy machine, true or false? You got a 50-50 shot. Somebody has to take it. What is it, Moore or Mealy? Moore, thank you. It's Moore because you've got outputs that are a function only of state, not of the input. So that makes it a synchronous Moore machine. And our states are numbered 0 through 6. So next states are for x equal 0 and x equal 1, and then we'll have an output. So if you're in state 0 and you get a 0, your next state is 5, and otherwise it's 2. If you're in state 1, you're going to get next states 0 and 1. If you're in state 2, your next states are going to be 0 and 5. If you're in state 3, your next states will be 0 and 1. For state 4, your next state is going to be 0 and 5. For state 5, your next state is going to be 0 and 5. For state 6, your next state is going to be 5 and 4. And the outputs are all 0. No, they're not. Outputs are 0 for state 0 and 6. Otherwise, they're 1. And that's what we got. So now, you want to do your implication chart. Although, there's an obvious row reduction here and here, and there. And you could do the row reduction first, but let's just do the implication chart. We'll go 0 through 5. And now we know that 0 is different from 1 through 5. One is different from 6. 2, 3, 4, and 5 are all different from 6. And that's the trivial differences. 0 may not be different from 6 since they both have the same outputs. So let's compare 0 and 6. It's true if 2 is equal to 4. Let's compare 2 and 4. It's true. 2 is equal to 4. And so now let's look at 6 again. 0 and 6 are true if 5 equals 5, 2 equals 4. Yep. So 0 is equal to 6. So now I have 0 is equal to 6. 2 is equal to 4. Let's try 1 and 2. 0 equals 0. 1 equals 5. Well, we don't know if 1 equals 5. So let's compare 1 and 5. I got 0 and 0, 1 and 5, 1 and 1. So that looks good, which means 1 is equal to 5 and also equal to 2. Right? Because 1 is equal to 2 because 1 equals 5. Now we do 1 and 3, and that's looking equal. And then we'll do 1 and 4, which requires 1 and 5, which we have. So if 1 is equal to 4, then, and that's equal to 1, and 1 is also equal to 5, 2, and 3, then this whole thing is equal to 4, and that means I don't need this anymore. So 1, 2, 3, 4, and 5 are all equal, which is pretty cool. Then 2 and 3 are equal because 1 is equal to 5. And there's 2 and 3 anyway. 2 and 5 are equal, and you can see they're equal here as well. 3 and 4 are equal, and you can see they're equal here as well. 3 and 5 are equal. And you can see they're equal here and here as well. 4 and 5, those are equal. And we knew they were equal because of this. And so now we have 6. We have 5, 2, 3, and 4. And everywhere we see a 5, we can write a 1. And look how reduced that is. We're down to just 2 states. And let's see what we got here for number 6. Yeah, so number 6 doesn't show a correct answer, so none of the above is your best choice for number 6. But this is a correct answer, I think. So, any questions about number 6? Let's go back to the chat. Somebody said something about question 7. So we're getting questions on every single question. Let's get a fresh piece of paper. Okay, let's have a looky-loo. Oh boy. Here's question 7. It's a nice long question. And the goal is to reduce the state transition table. Now, if I start this, I don't think I'm going to have question 8 time. Question 8 time, we can do it in pretty short order. So since somebody asked about question 8, I'm going to skip question 7 and see if we can do question 8 first. And then I'll go back to question 7. Let's see. What do we got? What's this? Now, if you're reading the book, you can see this in the book. This is a register. You guys know what a DAC is, right? What's a DAC? Anyone want to chime in? That is correct. Yes, that's exactly right. So the digital to analog converter is taking in the parallel digital number in binary and giving us a voltage output. And so if you put in a number that goes from 0 through, let's say, 255, you'll get an output which goes from, let's say, 0 to 5 volts. That's what this stack does. And then it compares it against an input voltage which goes through a sample and hold. And when the comparator says the DAC is too low relative to the input voltage, it makes the register count up. And when the DAC is too high relative to the input voltage, it makes the DAC count down. And so this number here, this register, is an up-down counter, which is feeding the DAC. And what we want to do is we want to latch this number so that once it's time for us to see the end of the conversion flag come in, we will be able to get a number which gives us a number that corresponds to the voltage which is used on the input. This entire system is a successive approximation system. And what does this do? What is this? Well, if this is a DAC, what this does is the opposite of what a DAC does. What's the opposite of a digital to analog converter? I'm not getting anyone sort of participating in the chat here. Yep, that's an analog to digital converter. So the choices are, is it an ADC? Yes. Is it a successive approximation ADC? And the answer is yes. It's always chasing this voltage, always going up or down depending upon whether the voltage in or is higher or lower. And then it says a device that gives about 6 dB of signal-to-noise ratio per bit, and that's also true. So all three of these things is true, and that's why we write all of the above. Now, this is one of those you kind of have to read the book kind of things, but that is also an important feature that you will find built into the chip, which we call the Arduino Uno. So it has several inputs to a successive approximation A to D converter, so you can get analog signals into your little microcontroller. And this is a very typical sort of thing. I've built one myself just out of discrete resistors and an up-down counter, and it's very educational to do that. So you got to get your analog inputs into the computer somehow. So I'm talking to you on a microphone. Somewhere in this microphone is an analog to digital converter, perhaps just like this, at least in principle. This is a block diagram. And then you couldn't hear me if they didn't digitize my voice. So there you go. It's the secret to getting, it's the secret. It's no secret. It's a common technique used for getting analog signals into a digital computer. So that's question 8. Now somebody had said, can you do question 7? Let me just go back. Oh, and we also want to do 9 and 10. Well, question 7 was such a long one. Let's do, I think we're better off doing a couple of short ones than just doing a long one and not being able to finish it. And I'm pretty sure I can start the long one, but I'm not sure I can finish it. So why don't we do the short questions first? Since at least we'll be able to finish those. So it says here, getting the following load cell to work requires an ADC and a computer. An ADC stands for analog to digital converter. And what is it? I see this here is a strain gauge, and that's a strain gauge, and this is a strain gauge, and that's a strain gauge. But they're placed in a load cell which has an aluminum bar or some sort of flexible bar that's been bored out with a hole or 2 holes, and then they put in strain gauges in here and one in here. When one gets compressed, the other one is stretched, and then they'll put in a little strain gauge over in here, and then they'll have one on the other side. And so if it gets bent the other way, one will be compressed and the other one will be stretched. This voltmeter will measure the difference between the two, so you'll see how much something is stressed. And if you have this bar calibrated as a material property so that it will be in its elastic mode, then as it bends, it will go back into its original shape. That's what it means to have an elastic material. If you bend it and it stays bent, then you have had what's called plastic deformation. The point at which you bend it and it no longer returns to the original shape, that is known as the yield strength of the material. Well, what the people do is when they're looking to see if something has been stretched to the point of its yield strength, is they put on these strain gauges, and you can do it for bridges, you can do it for buildings, you can do it for helicopters, you can do it for any structure, and it will determine if there is going to be a so-called failure mode. In the case of something as simple as bookshelves, we'll just put a piece of wood out, and then we'll load it up with books. A bunch of books sitting on the shelves. And eventually you'll have what's called engineering creep. And these things will start to bend and bow, especially if they're particle board, until eventually they break. If you instrument them with these strain gauges, you'll tell how much they're bending. And that's the key. So this is a strain gauge established in a thing called a Whitestone bridge. And do you need a computer? Do you need an 880 converter? And the answer is no. A battery and a voltmeter is all you really need. And so to get a load cell to work like this, you really don't need a computer. But it's very nice if you have one, because then you can digitize the information and send it to, I don't know, Bridge Monitoring Central to see if the bridge is going to fall down. So that's sort of a useful device. And if you take the microcontrollers course, you'll encounter this. The next one up, number 10. Number 10 says, what's this? Anyone care to hazard a guess? All of the above, yes, is correct. It is a sample and hold. The analog input goes through a buffer op amp, and then that charges this capacitor C, and then this buffered op amp hopefully will not discharge the capacitor as you read the analog output voltage. And so this little doodad right in here, that turns on and off the sampling. So if you go back over here, that's the sample and hold. And so your sample and hold from your successive approximation analog to digital converter is right here. And this is called a zero order sample and hold. And so now when you read this zero order, right? So what does zero order mean? What it means is when you have a nice smooth sine wave and you sample at regular intervals, uniform intervals, you make a little square wave here. So you're basically making a square wave approximation to the sine wave. That's a zero order hold. A first order hold would try and use a little triangle going up. Maybe higher order holds would have little curves. So that's a zero order hold, and it's done with this capacitor and a couple of buffer op amps. And that, I think, is all you need for the whole homework, except for the one thing which I skipped and said I would get back to, but unfortunately we don't have enough time to finish it because it's big. And that is question number 7. Were there any questions about the sample and hold? We can try. Yes, we can certainly try. I'm not going to rush it though, because I'll probably mess it up. So let's do the present state. A, B, C, D, E, F, G, H. Let's do the next state. X equals 0, X equals 1, H, C, C, D, H, B, E, it's not E, it's F. And now we got to do the output for x equals 0 and x equals 1. Okay, is it a Moore machine or a Mealy machine? Mealy is correct, right? Because why? Because the output is a function of the input. So that means this is an asynchronous machine. All right, let's have a look at this. We'll start with B and go to H. Now we're going to start with A and go to G. And now what we'll do is we'll take a look at the outputs. A is different from B, E, and that's it. B is different from C, D, F, and G. C is different from E. D is different from E. E is different from F, G, and H. F is different from G and H. And G is... oh, no, maybe it's not. F is not different from G and H. All right, because it's 0 on outputs. We don't know about that. So that's what I have so far. 4 minutes to go. I don't think I can finish. A through C, H is equal to H. That's correct. Does B equal to C? It does not. And therefore, put an X in here. Let's look at A and D. Does F equal H? We don't know. Does C equal H? We don't know. But wait a minute, the outputs are different. Did we miss something here? A is different from B, C, D, E, and F. Right? Because we have to look at both outputs. Let's see, B is different from G and H. C is different from G and H. D is different from G and H. E, yeah, we already have it's different from G and H. And F has to be different from G and H, so this does get an X. Darn it. And G could be the same as H, we don't know. So that actually eliminated quite a bit. Let's take a look again. Is A the same as G? If G is the same as H, we don't know about that. If C is the same as C, if 1 equals 1, 0 equals 0, so A equals G if H equals G. Does H equal G? We don't know. H equals G if G equals A. So that looks pretty good. Circular. So A is equal to G and H is equal to G. And now what about A and H? Well, A must be equal to H, right? AH, CC, yep. Because of this. So what about B and E? How am I doing on time? Oh boy, we're out of time. Is D and F equal? And the answer is we don't know. And if we go to DF, we get FF, GH. That's true. So D and F are equal. And now B is equal to E. And what about C and D? C and D, it's true if F equals H. It does not. And C and F. C and F says F has to be equal to H, but it does not. So this is what I have, and that is the answer to, that'll give you an answer to question 7. So that's what I have for today. I think we have no more time. If anybody has any questions, I'm here. Any questions about what I just did here? I think that pretty much wraps up homework 12, and you've got a final to look at. So prepare your questions for next Thursday. Take a look at that final, and I thank you all. Have a good day. Bye-bye. Thank you.